Hello, my name is Dan Brunner, and in this video, I'll be going over how to solve problem 9.028 in Chapter 9 of the Fundamentals of Mass and Heat Transfer textbook. So looking at the problem statement, we have an electrical heater in the form of a horizontal disk. This heater has a diameter of 500 millimeters, and it's used to heat the bottom of a tank filled with engine oil at a temperature of 10 degrees Celsius. And we're trying to find the power required to maintain the heater surface temperature at 65 degrees Celsius. So we're given the tank diameter, the ambient temperature of the fluid inside of the tank, and then the surface temperature requirement for the heater. And we're asked to find the power generation of the heater. So to do that, we need to make some assumptions, including that the system has reached steady state conditions. We're looking at constant properties for the fluid. The engine oil, which is the fluid, is initially quiescent, meaning that it is not experiencing any convection. Initially, we have negligible net radiation, and the system is closed. We have insulated walls, so no heat is being transferred out of the tank. So for our governing equations, we have the characteristic length for this specific scenario given by the surface area of the cylinder divided by its perimeter. We also have the Grashof number, the Prandtl number, and ultimately these two dimensionless numbers will be used to calculate the Rayleigh number. And then the Rayleigh number will be used to calculate the Nusselt number. The Nusselt number will then be used to solve for the convection coefficient, where you have the Nusselt number times the conductivity of the fluid divided by the characteristic length here. So the surface area divided by the perimeter. And then we need to find the convective heat transfer rate. So that's given by the convection coefficient times the area times the change in temperature. So let's see here. Another key assumption that we're making is that, well, we have constant fluid properties. And so to find the properties of the engine oil, we look at the mean temperature, which is 310 Kelvin, and we evaluate the properties of the engine oil using table A5. And those properties you can see right here. Oddly enough, if you use the Prandtl number that's given in table A5 at that temperature, 310 Kelvin, you don't get the same answer as when you use the equation for the Prandtl number, which is the kinematic viscosity divided by the thermal diffusivity. So that's the version, or those are the table values that we'll be using, and that is what matches the solution guide. So first we calculate the Grashof number. We get a very large number for the Grashof number. Again, the characteristic length here, L, is equal to the surface area divided by the perimeter of the tank. And then we can go ahead and calculate the Rayleigh number. And so we just multiply the Grashof number by the kinematic viscosity divided by the thermal diffusivity, and we get around 3 times 10 to the 7th, which is between this range for the Rayleigh number. And therefore, we can use this Nusselt correlation. And this is specifically for the upper surface of a hot plate, which is, very, very good for the situation that we're trying to analyze. So once we have the Nusselt number, we can calculate the average convection coefficient. So I'm getting 54.2. This does match the solution guide. And then calculating the total heat transfer rate due to convection, we get a heat transfer rate of 585.2 watts. And if we were to plug this into an energy balance using the heater only as our control volume, we get that the heater needs to produce a power value that is equal to the convection heat transfer rate. And so the power that the heater needs to generate is also 585.2 watts. And that is how you solve problem 9.028. Thank you.